Thanks for welcome everybody, and thanks for joining today's ARISE seminar. I'm Ana Capuano, Professor of Biostatistics in the Department of Neurology and Public Health Science at the University of Chicago. And today we continue our ARISE series featuring developments of early career scientists on data science. We will begin with Dr. Xuanxin Wu, that is a postdoc research scientist at the Mailman School of Public Health from the Columbia University. She will present the work advised by Lindsay Kobayashi. She will present how a probabilistic bias analysis can test whether the observed gender difference in the link between loneliness and memory decline reflects real effect modification or differential underreporting of loneliness. This work is published in the AGE in 2024 and is a template for handling misclassification when there is no perfect gold standard. Our next speaker will be Margaret Guerchero, a PhD student in the Department of Biostatistics of Columbia University. She will present the work mentored by Dr. Xianzhu Li. Margaret introduces a Bayesian longitudinal CCA that integrates trajectories across imaging modalities, robust to small samples, uneven visit spacing, and missiness, motivated by EDNI to illustrate how pathology and structure co-evolve in Alzheimer's disease. And then our last speaker will be Matthew Scott, PhD candidate in the Department of Biostatistics of Boston University, advised by Dr. Yorgos Tripodis, that joined us today. Matthew applies Wiener process-based degradation models to ALS clinical trial data, cleanly separating within person variability, measurement error, and progression, an approach with clear implications to modeling cognitive and functional decline in aging cohorts. So each talk is going to be 15 minutes, and we are taking all the questions at the Q&A at the end. That we'll also have some discussions. So let's get started.
Can you see my slides, everyone? Not in presentation mode, all right.
Yeah, good.
Thank you so much for the introduction. I'm so excited to be here for this presentation. This is part of my dissertation research that was completed at the University of Michigan, and I include the data code in my personal GitHub as well as the supplement in this research article. Loneliness is a growing public health concern, and my previous study has found that cumulative loneliness from 1994 to 2006 was associated with a faster rate of decline in the subsequent 12 years among middle-aged and older adults in the United States. And I also find that the association was actually stronger among women rather than men. This picture here shows the memory trajectory among men and women separately across each of the loneliness duration group. The fourth solid line on the top represents women, and the fourth dashed line on the bottom represents men. We can see that compared to men, women experienced a steeper memory decline due to loneliness duration. However, this effect modification was not consistent with previous research, which did not observe gender-specific association between loneliness and dementia risk. This is potentially because we use the single loneliness item from CESD scale, which asks the participants, do you feel lonely, in the H1S one-on-one research interviews. In research interviews, potentially due to social desirability bias, men may be less likely to admit negative emotions, including loneliness, leading to the observed effect modification, which can be biased. However, this possibility is difficult to verify because loneliness is a subjective measure, and there is no objective golden standard data to validate against its self-report. So I propose this probabilistic bias analysis to aims to quantify the potential magnitude and direction of information bias arising from loneliness underreport between men and women. In general, the general concept of my probabilistic bias analysis is that we assume men had lower sensitivity values in its loneliness measure compared to women. And based on this assumption, we conduct a record level correction that corrects the loneliness status for everyone at each time point in our study sample, and then repeat the analysis that I have done in my previous research to see how much chance do we still have to observe the effect modification. And now I'm going to talk about the first step, which is about specifying the sensitivity and specificity values of loneliness measure. Although there's no golden standard data to validate against self-report loneliness, we conduct this validation study using 3-item UCLA loneliness scale in HRS psychosocial and lifestyle questionnaire as the best available golden standard for 2 reasons. The first one is this questionnaire was left behind after HRS men co-interviews. The participants were required to answer this question privately using pen and paper, and then mail back their answers to HRS. So data from leave behind questionnaire should be less likely subject to social desirability bias compared to our single CESD item. In addition, the UCLA loneliness scale has 3 questions with Likert style response options. Therefore, it comprehensively captures the loneliness status compared to our single CESD item. So we conduct this 2x2 tabulation with the observed loneliness as our main variable, and then use the true exposure derived from the UCLA loneliness scale. We used a cutoff value of 6 to classify individuals as truly lonely and truly non-lonely to calculate the sensitivity and specificity values of the single CESD item. And this table shows the result from this validation study. We observed a high specificity value among both men and women, suggesting that loneliness over-reporting is unlikely. And as it's beyond the scope of our study, we specify the specificity values all ranging from 0.92 to 1 in all simulation situations I will talk about later. And then for sensitivity values, we find that men had lower sensitivity values compared to women, about 0.1 differences. This informed our first simulation scenario, where we're holding the sensitivity values between men and women constantly at 0.1, and we have the 7 situations on the first simulation scenario. Each row represents 1 situation, and across these 7 situations, we allow the sensitivity values among both men and women increased over a wide range. And in order to test all plausible magnitude of loneliness underreport, we additionally simulate 2 scenarios. The second scenario, as shown here, we hold the sensitivity values among men at a very low level, ranging from 0.3 to 0.35 across all 7 situations, and we allow the sensitivity values among women increase from 0.3 to 0.95. These scenarios simulate situations where men had a low propensity to admit loneliness, and the extent to which the differences between the loneliness underreporting between men and women would meaningfully bias the effect estimate. And the third scenario is completely from the second one, where we hold the sensitivity values among women at a very high level, ranging from 0.95 to 1. And then we allow the sensitivity values among men range from 0.25 to 0.9. This scenario simulates situations when women did not underreport their loneliness status, and the extent to which the loneliness underreport among men will bias the effect modification. We made 2 assumptions here for simplicity. The first one is we assume that the loneliness misclassification was non-differential by memory outcome within each group, because exposure misclassification by outcome, in addition to an effect modifier, will substantially increase the computational intensity. In addition, we assume that the Bayes parameter, which are sensitivity and specificity values, are constant over the exposure period from 1996 to 2004 in each specified situations, because we did not find strong evidence about the age differences in loneliness underreport or overreport. And then based on the specified ranges of the sensitivity and specificity values, we conduct the Monte Carlo technique to randomly select a value from the range to calculate negative predictive value and positive predictive value. These values reflect the measurement accuracy in our study sample because it takes into account the loneliness distribution across memory outcome in HRS. And then we conduct the record level correction, which means at each observation, we correct the loneliness status based on the probability so that we generate a data set, which is assumed to be Bayes adjusted. Based on this new data set, we repeat the analysis in my previous study. So first, I conduct a subgroup analysis by men and women separately to demonstrate the direction of information bias among men and women separately. I fit the mixed event linear regression model and include a two-way interaction between loneliness duration and year to reflect the association between loneliness duration and memory decline. And then I conduct a pooled analysis by including the three-way interaction between loneliness duration, years of follow-up, and sex gender, which is beta 7 here, to reflect the effect modification. And the equations here use loneliness duration as a continuous variable, but we repeat all the analysis coding the loneliness duration as a categorical variable consistent with previous study. Because we replicate step 2 to 4 10,000 times, so we were able to generate the simulation interval. Overall, we have 3 simulation scenarios. Each of them have 7 situations, and then we conduct the Bayes analysis for each of these situations. Here is the results from the subgroup analysis between men and women separately using loneliness duration as a continuous variable. This is about the alpha 3 as shown here in the equation. The X bar here represents the sensitivity values specified in each of these situations. And then we also have the unadjusted alpha 3 from the original, from my previous research. This alpha 3 is below the null, showing that a longer duration of loneliness was associated with a faster rate of decline. And we have the other purple line here suggesting the simulation estimate and interval. So the direction of the Bayes is from left to right. We see that among both men and women, the loneliness underreporting bias the estimate towards the null. But actually, we find that the magnitude of the information bias was actually larger among women, even in the same sensitivity values. This is potentially because the magnitude of absolute value for the estimate among women is larger, so it has more space to move around or towards the null. And then we show the pooled analysis, which is about beta 7 in the first simulation scenario. The X bar here shows the sensitivity values for men. And because there is constant 0.1 differences between women, so we did not show the sensitivity values for women here. And we also have the original beta 7 in my previous research showing that the association was stronger among women. And we have this purple line here from the simulation. We count the proportion of this beta 7 below the null as the likelihood of observing effect modification. We find that across the 7 situations in the first simulation scenario, we have over 96% likelihood of observing effect modification by gender. As for the second scenario, we find the same likelihood as high as over 94%, so as the third simulation scenario. So when coding loneliness duration as a continuous variable across all simulation scenarios, the likelihood of observing effect modification by gender remained as high as over 90%, suggesting that loneliness underreporting is unlikely due to loneliness effect modification is unlikely due to loneliness underreporting. However, when coding the loneliness duration as a categorical variable, we have the three unadjusted estimates here from our previous research. From top to bottom, they represent loneliness at 1 time point, 2 time point, and 3 time points. We use the never as the reference group, and we also have the simulation estimate from the subgroup analysis. And at this time, we find that the direction of bias was not always towards the null, especially among the middle categorical group among women. But we also find that for the highest exposure group, the direction of the bias is always towards the null. And then we conduct a pooled analysis. We find that the effect modification was largely driven by the highest exposure group, which is loneliness at 3 or more time points. And this is consistent with the first simulation scenario, the second one, and the third one. So overall, we find that when coding loneliness as a categorical variable, the direction of the bias was unpredictable and complex for the middle level of the exposure group. These findings are consistent with previous research suggesting that the direction of the bias for categorical exposure misclassification is difficult to predict, and it depends on many factors, including the exposure distribution, misclassification rate, and the effect size. This may have important implications for population and clinical studies, as it's not uncommon to categorize a continuous variable using certain cutoff values, such as BMI and dietary intake. So we should not always rely on the bias towards the null heuristic. Overall, we find that the observed effect modification by gender is unlikely due to the loneliness underreporting, although we see their complexity when coding loneliness as a continuous variable versus categorical variable. And although there is analysis that investigate exposure misclassification by outcome, to the best of our knowledge, this is one of the first that investigate exposure misclassification according to an effect modifier, like sex and gender in our group. And finally, we provide a probabilistic bias analysis approach to examine the information bias when the exposure is a subjective measure with no golden standard data to validate against. And we include the data code for this bias analysis with record level correction that can be used when the exposure is longitudinal repeated measure. I would like to thank my co-authors, including my fantastic cohort fellows, dissertation committee members, and PhD advisor Lindsay Kobayashi. And thank you. I'm happy to take questions later.
Thank you. Let's move to the next talk now.
You can see my screen. Good afternoon, everybody. My name is Margaret, and today I'll be presenting my work titled Bayesian Longitudinal Canonical Correlation Analysis. And this work has been in collaboration with Dr. Sinjuli at the Mailman School of Public Health in the Department of Biostatistics. So starting out with the motivation for this project, in psychiatry, we find that a lot of conditions are likely to be connected to multiple biological processes. Lately, we've seen there's the availability of large-scale observational study, for example, the ADNI study, where they collect demographic, neuropsychological, genetic, neuroimaging data. And with all this information available, it's important to be able to extract complementary information from different sources in order to predict disease state and understand the mechanisms involved. So for example, at the ADME study, information is collected over time on the elderly individuals. And in that case, we would be interested in examining the trajectory and changes or patterns of Alzheimer's disease over time. So with the goal in mind of integrating and extracting shared information, we turn to canonical correlation analysis. So CCA is a tool used to discover joint multivariate relationships among different modalities. Over the years, different variants of CCA have been developed, but for the purpose of our work, we focus on the Bayesian techniques, mostly because they offer certain advantages over the frequentist approaches. So first I'll start out with an overview of Bayesian CCA when we have cross-sectional data. So Bayesian CCA involves formulating a latent variable model between two observed modalities, Y1 and Y2, and those are represented here by the rectangles. So in Bayesian CCA, we have this shared latent variable Z that is shared between our two observed modalities. And then we have these modality-specific latent variables Z1 and Z2 that are only relevant to their respective observed modality. So putting it all together, you end up with a model where our observed Y is has a multivariate normal distribution, where the mean is a summation of the shared parts and the non-shared parts with a generic covariance matrix. For the sake of the rest of the presentation, whenever you see A, just think that's the projection matrix associated with the shared latent component Z, and the B's represent the projection matrix C's for the non-shared components Z1 and Z2. Looking at the literature, we see that there are issues that are encountered with CCA methods when when data is collected over time. In the literature, we see that there are existing methods, but they are in the frequentist framework. The first set of CCA methods that were developed were created in the context of genetic neuroimaging, but they have some key limitations. So they are unable to handle unequal time gaps or temporal misalignment. So essentially, if your data is not collected at the same time for both modalities or have the same number of visits, those methods can have issues. So in order to combat those limitations, longitudinal canonical correlation analysis was developed, so LCCA. However, LCCA is a two-step process, which means that the algorithm is highly dependent on the first step. So sometimes small but important signals might be missed due to the fact that the model is estimated in a two-step manner. And then the other limitation is that it requires a moderate sample size to obtain stable results. So for us, in order to combat those limitations for longitudinal data, we formulated a unified Bayesian longitudinal CCA model that can incorporate data from multiple time points. So here I'll start out by here I'm presenting the proposed model, which we named Bayesian Longitudinal CCA, BLCCA for short. For the notation, let Y sub nj k represent the observed p-dimensional vector in a specific modality for a specific individual at a specific visit. So the k represents the number of modalities you are dealing with. N is for the individual, and J is for a particular visit. Now here I'm giving a visual representation of what BLCCA looks like. So this is a two-level process. We start out with the observed data here at the bottom. To the left here, we have the data collected for the first modality across J visits. And to the right, this is the data collected for modality K across J visits. For the sake of this presentation, we are dealing with when K is 2. So the first level of BLCCA is taking our observed data and transforming it into linear trajectories that we are labeling as these DK. So the question is, how do we do this? And we do this using a random intercept and slope model, where we define our observed data YK as a summation of the random intercepts and the random slopes and some error here. Then in the second layer, we take those linear trajectories, those DKs that we found, and we perform Bayesian CCA as I presented it early in the presentation. So you find our shared Z between our linear trajectories and also the modality specific Z's. So then here now we define our linear trajectories DK as a summation of the shared parts and the non-shared parts. Finally, to deal with identifiability issues related to component allocation, we concatenate the projection matrices. So now concatenating the matrices help with reducing the number of projection matrices that you have to estimate. So instead of having to estimate A1, B1, A2, B2 separately, now you can just estimate all of them in one go with this matrix that we are calling W0. And we repeat this process for the matrix associated with the random intercepts and also the random slopes. One unique thing about this matrix is that it has a specific block structure. So you see that there are some blocks that are zeros. So essentially, when a certain block entry is not associated with a particular modality, that's when we set it to 0. So here the first couple of rows represent the entries that are associated with the first modality, and then the last couple of rows are the entries associated with the second modality. Since we concatenate the projection matrices, we also have to do it for their associated latent variable Z's. So we put the shared Z and the non-shared Z1 and Z2 together, and we end up with this concatenated Z here. So now putting it all together, from that visualization I showed, you end up where the model can be written as the observed Y for an individual N at visit J has a multivariate normal distribution, where this mean is a linear function of the Bayesian CCA that is performed on the random intercepts and the Bayesian CCA being performed on the random slopes. And here our covariance matrix is diagonal, where the precision values are a tau k. And finally, our concatenated latent variable Z's have a standard normal distribution, RC. And RC basically represents how many columns will be in our W matrices. So to estimate our parameters, we first place conjugate priors on them. The most important prior to pay attention to is this prior for the columns in W. And essentially here we use an AIR-D prior, which automatically selects which column in a modality is not selected by pushing the respective precision value to a large number. So essentially what that's saying is that if our precision value alpha is really large, that means that the values in that column of W will approach 0 and will be deemed as non-active. But then if the alpha is really small, then the values in that column will be what we deem active and will have non-zero values. Since we are using conjugate priors, we're able to obtain a closed form conditional posteriors. and we use mean variational inference to approximate the posterior distribution. We can also use the typical MCMC algorithms, since particularly Gibbs, because we have the closed form condition of posteriors, but variational inference does have its benefits in terms of computational time, but also in helping with some identifiability issue with the rotation matrix. So to give like a intuitive look into what the model looks like and the results it gives, I will I'll go through a toy example. So here we are assuming we are collecting information for two different modalities, Y1 and Y2, and we collect data across J visits. We have 100 individuals in our sample, and for the modality 1 and modality 2, we collect 25 variables. Then we assume that the true underlying variables in CC have dimension of 4, and 2 of those 4 will be shared, and 1 will be non-shared for each modality. So here's the first look into what the algorithm spits out. So to the left, I'm showing you what the true latent components for Z look like. So the first two are curves, and these represents the shared components, and the last two represents the modality specific one. And then to the right, I'm showing what the algorithm was able to estimate. And as we can see just from a visual check, the BLCCA is able to retrieve the components fairly well, and it's able to identify those shared ones as well as those modality specific. The second thing is the BLCCA model was able to reduce our dimension from when we started with those 25 variables for each modality, and now it's able to identify the true number of components, which is 4. Unfortunately, in a real world situation, we wouldn't know the truth, so we wouldn't have these curves on the left. So we need another way to be able to differentiate between those who are shared and those who are non-shared. And we do this by using the precision values alpha as a guide. So the rule is when you have a low alpha value, then that should indicate that that column is active. But then if your alpha value is really high, that will indicate that that column is approaching 0. So the first step is identify which alpha values are relatively low. So those are shown in the bold here. So we do that for the alpha value associated with the projection matrix for the random intercepts, and also the alpha values associated with the random slopes. Okay, and then the second rule is that for a component to be considered shared, it must have a low precision value for both modalities. So we can see that's relevant to component 1 and 2. So here the alpha values are low for dataset 1 and 2 for the random intercepts, and it's the same thing for the random slopes. And then the last rule is
Margaret, 1 minute.
1 minute?
Yeah.
Okay, yeah. So that is non-shared when it's only small for a specific component. So we see that's relevant for 3. In situations where it's unclear if alpha value is low, then we can use the projection matrix as a decision factor. So here I'll briefly show results from a simulation study. So we looked at 100 data sets from a sample size of 10 to 250, and did this for 2 data settings where one, we have 25 variables, and the second, we have 50 variables. Here I show the correlation, just seeing if we were able to recover our estimated Z's. And the box represents the correlation between the true and estimated. And the main takeaway here is the correlations are fairly high for the shared and non-shared, and also for the non-specific. And then the other really important thing to note is The model performs still fairly well when even the sample size is as small as 10. So finally, the main takeaways of this project is we were able to formulate a BLCCA model that can handle longitudinal data. It models the two processes jointly, and it produces stable results when we have sample sizes. Lastly, we are able to uncover the true dimension of the latent space, and we do not need to pre-select the dimension of the latent structure. So we don't need to pre-select RC. The model can do that on its own. And lastly, we can identify and discriminate between those shared patterns and distinctive features of the data sources. Lastly, since we use variational inference, our model is computationally fast. So in theory, this can be scaled to a large P, but in reality, we do have to consider the dimension of the Z. So RC does also influence the runtime. That's the end of my presentation. Thank you.
Thank you. Now let's go to our last presentation.
Can that be seen? All right. Hi, everyone. My name is Matt Scott. I am a PhD candidate at Boston University in biostatistics, and my talk is titled Assessment of Wiener Process Degradation Models with Application to ALS Decline. So first, I will give a brief background on degradation models. As a motivating example, I will then discuss a simple degradation model for one patient. Then I'll present degradation models across multiple patients that can be used in practice. For validation, we then run a numerical study in clinically relevant simulation settings. For a proof of concept of these models, we apply these to estimating ALS decline, followed by concluding remarks. So degradation models view deterioration as a continuous time stochastic process, such as a Wiener process, gamma process, inverse Gaussian process, whose increments capture random decline. This class of models may be useful in clinically relevant settings as they capture within subject heterogeneity more explicitly than standard longitudinal analysis methods. Recent work has shown that utilizing stochastic components can result in improved model fit and prediction compared to conventional mixed effect models, and as such, this work evaluates Wiener process-based degradation models with multiple sources of variability, estimation methods that stabilize covariance matrix inversion, as well as profile likelihood methods that reduce the dimension of parameter search are presented in validating using Monte Carlo simulations. As a proof of concept, we apply these methods to ALS decline to see if these models parallel expected patterns of decline. For a motivating example, we first present a simple Wiener process within one patient. If we let y be a disease trajectory, then for the continuous process yt with initial condition 0, consider the SDE dyt equals mu dt plus sigma dwt. For those of you who may not be familiar, W is known as a Wiener process, or also known as Brownian motion. It is a process that is normally distributed with variance that's a function of time and whose increments are independent. So when you actually solve this equation, we get that the process is equal to a linear trend plus the Wiener process. Then taking this at discrete time intervals, we see that y is normally distributed with the mean equal to a linear trend and the variance equal to the Wiener process times this matrix lambda, whose components correspond to minimum time entries of the minimum cross-entry times. To visualize this, we have simulations of this process in both continuous and discrete time. For both plots, the main takeaway are that there is a linear trend, and then for the variance, this tends to increase as a function of time. The covariance matrix is singular, so first differences are taken to stabilize it. So if we let V be the first difference in the outcome and tau be the first differences in time, the resulting distribution for V changes from Y in that the mean is now a trend based on the change in time, and the covariance matrix is simplified, and we just end up with this matrix S that's simply the diagonal entries of the changes in time. MLEs are straightforward to derive from here, and we see that the information for mu is proportional to the length of the observation period, and then the information for the variance is proportional to the number of sampling times for the process. For practical application, we must look at this process across multiple patients though. So if we let I be our patient indicator, TI be the follow-up times, and YI be their outcome collected at visit J. The Wiener process alone is not sufficient for most clinical applications, so we introduce a random slope term to account for between subject heterogeneity in the slope, as well as a measurement error term. So then for the ith patient, the model that becomes normally distributed with the same slope and Wiener process variance as before. However, we have these components here that are the random slope as well as the measurement error for the variance. Taking differences as we did before, we again let tau denote change in time and v denote change in the outcome. The first difference model results in a normal distribution with a linear slope by change in time for the mean, along with difference Wiener process, random slope, and measurement error terms for the covariance. Just to note, A here is something called a tridiagonal Toeplitz matrix. I won't get too into it now for the purposes of this talk, but just note that this class of matrices has been studied extensively. So when working with this matrix in practice, we have very nice efficient inversion properties and algorithms that can make our lives easier. As this is a Gaussian family, we can construct a likelihood as shown below. This also allows for inference, where we can construct walled confidence intervals for individual parameters, as well as differences in slopes between groups, and also compare models using likelihood ratio tests and information criterion. So our goal was to examine in a stepwise fashion 3 common sources of variability observed in progressive data while maintaining analytic tractability under first difference estimators. So the first model, M1, this uses only the Wiener process variance and the linear slope, as we saw in our first example, just across multiple patients. For model 2, this additionally incorporates between subject variability of the slope. And then lastly, for model 3, this also introduces the measurement error term. For estimation, deriving MLEs for M1 shows that each parameter is a weighted average of its individual level Wiener process estimates, with the slope being a weighted average of the follow-up times and the Wiener process variance being a weighted average of the follow-up frequency. For model 2, this is also a weighted average. However, it's weighted average for the slope. However, due to the increased computational complexity, we can do profile likelihood over the 2 variance parameters that's required. For Model 3, we can utilize a similar approach to Whitmore. Whitmore proposed a efficient profile likelihood method over a ratio of variance parameters when introducing measurement error to a Wiener process. This paper was one of the first degradation models proposed back in the 90s, but we can still use similar concepts today. And these concepts of profile likelihood are still being used a lot in these degradation models. But essentially, we're using a similar concept here. We're doing a profile likelihood over a ratio of the measurement error to the Wiener process variance terms. And then from here, we can get direct estimation of the unconditional MLEs for the remaining parameters. This essentially reduces a 4-dimensional optimization problem to just a 1-dimensional search. And just to note, empirically unbiased estimators similar to these have also been proposed by Tang et al. 2022. And these propose a adjustment to the variance parameters, which are particularly useful at smaller samples. Additional simplification extensions can also be made. So for example, one simplification can be made when assuming conditions similar when equal follow-up durations are met in, for example, a randomized control trial. So you can see the inversion and determinant of D simplified to these equations here, where R and S are characteristic roots stemming from a known recurrence relation of a general tridiagonal Toeplitz matrix. This class of models can also be connected into mixed effect frameworks to incorporate flexible fixed effect covariates and Raman effects. And this also allows us to use the standard modern machinery that is efficient MLE estimation. So to identify the identifiability, to validate the identifiability and consistency of these models, we perform Monte Carlo simulations 1,000 times under both unequal and equal follow-up for 100 patients. Equal follow-up times were generated using time equal to 0 to 10 for each patient. Then for unequal follow-up, we generated follow-up times using the following scheme. So first we generated the number of follow-up visits from a discrete uniform distribution with bounds between 3 and 10. Then we sampled from a continuous uniform distribution that's bound between 0.5 and 1.5 NI times. With these sample values, we calculated the cumulative sum and then subtracted the first recorded times, making the baseline time equal to 0. For estimation, we calculated profile MLEs and empirically unbiased estimators. And then we also compared this to a boundary corrected optimizer using the full joint likelihood. Here are the results for the equal follow-up simulations. So models 1 and 3 are shown in rows, and the estimation method is shown in the columns. Across the board, all estimation methods for each model perform well. For example, the coverage probabilities were between 0.94 and 0.96 for all models and estimation types, and the largest relative error was about 1.5 for the random slope variance in Model 2 and Model 3. Under unequal follow-up, where patients had both variable number of follow-up visits and variable duration between these visits, there were no issues with estimation under the full joint likelihood. However, for Model 3, using the two profile likelihood methods, the coverage probability and relative error were problematic for the Wiener process and measurement error variance components. For example, the relative error for the profile LME of the Wiener process was 27%, with a coverage of 0.79. And that was in the LME for the Model 3 down here. And just to note, omitted for this talk, but upon further investigation, we found that a lot of these spikes in relative error and coverage probability for the profile likelihood methods were largely driven by patients that had highly clustered follow-up times, but more methods need to be developed to address that. So as a proof of concept, we apply our models to ALS data. For our data source, we use PROACT data. This is the largest publicly available ALS clinical trials database. For our outcome measure, we use the ALS Functional Rating Scale, the revised version, or the ALS FRSR for short. This is a 12-item composite with scores ranging from 0 to 48, with higher scores indicating better function. For inclusion, we only included placebo-arm patients with defined FRS, the status, and time data. And for exclusions, we excluded individuals who were older than 80 years old, who had more than 3 years of symptom duration, and who had less than 3 follow-up visits. The resulting sample resulted in 588 individuals, of whom 291 were alive and 297 died within the duration of the study. Results for each model and estimation technique is shown across all patients, as well as when stratified by vital status. Based on model fit statistics, the best model was found to be M3 with the joint likelihood across each group, where there was found to be a decrease in the FRS at a rate of 1.22 units per month in the full sample. As expected, patients who are alive declined in FRS at a rate of 0.82 units per month, slower than patients who died. And these findings are consistent of what we would expect with ALS decline, indicating that our models are giving reliable estimation. So in conclusion, degradation models may be an alternative to conventional longitudinal data analysis methods by explicitly accounting for underlying time continuous stochastic process that efficiently accounts for within subject heterogeneity and provide interpretable estimates. First difference estimators showed reliable estimation based on Monte Carlo simulations. Profile likelihood methods exhibited stable estimation as well, but this might require further scrutiny when using data with high temporal clustering. In clinical data, Wiener process degradation models mirrored expected patterns of ALS decline. Just to note some limitations and current work in progress. So this work requires a Wiener process assumption. Future work should investigate other Gaussian processes that have been shown to improve model fit, for example, integrated Brownian motion. Then beyond the Gaussian distribution assumption, non-normal degradation models such as gamma process, inverse Gaussian process, and heavy-tailed student T process variants should be explored, as they may better capture monotone deterioration, jump-like increments, and outlier-prone noise when normality is doubtful. Then we hope to investigate ways to stabilize profile likelihood estimation when there's high temporal clustering. And then lastly, as an initial step in understanding how degradation models behave in relation to ALS mortality, we stratify by death status. However, this is obviously not completely sufficient. So models that explicitly account for more survival-related issues are definitely needed. And that's something we're working on now, incorporating these types of models into a joint multi-state framework. Lastly, I would just like to thank my mentors, Yorgos, Alex, and Kendra for the help on this project, as well as the Arise leadership for this opportunity.
Very good. We now open the floor for the questions. We already have one question in the Q&A. So please add questions so we can, enrich the, the presentation. So the first question is, what is the rationale for considering loneliness duration a categorical variable? And together with that, I would like also to ask the rationale for the cutoff of 6, right? Cutoffs are always complicated you have to justify them, but so.
I'm not sure whether it's asking for the cutoff value of 6 in the validation. If it's for that, we use it consistent with the previous study that showed that a cutoff value of 6 could divide the clinically meaningful loneliness status. And if it's for the main exposure loneliness duration, which we measure loneliness over the 8 years, which has 5 interview waves. So at each wave, we classify individuals as yes or no, and then we count the number of waves, whether they report loneliness ranging from 0 to 5. And we classify that into never being loneliness at 1 time point, 2 time points, and 3 time points, or more, only because we would like to test potential nonlinear or dose response association between loneliness duration and memory decline. Thank you.
Very good. So in the rationale behind classification of loneliness, why do we want to classify? Well, usually, so I would say that usually we like to look things in the continuum to understand etiology, right? And that's more rich. We usually don't miss information, right? When every time we aggregate data, we end up losing information, right? Classification is very helpful when you're trying to address in the clinic, right, problems. So you put people in pockets to then try to guide treatments, and so those classifications are important. Specifically in loneliness, do you have any comment on why classification is important?
Yeah, because during COVID pandemic, we see a large proportion of older adults or even younger adults experience loneliness, but that was a very short period of time. So everyone at some time point experienced loneliness. So we would like to test whether being sustained in loneliness compared to those only in 1 time point, whether there are differences in population outcomes. So that's the main reason that drive us to classify loneliness. And it's like the result also show that being loneliness at one time point, the effect can be very minimal. So we're like, it's a good result that we are okay that if we all feel lonely during COVID-19 pandemic.
It's sustained is not good, right?
Yeah.
Okay, so I have while I wait. Thank you. Please put questions on the Q&A, and I will let anyone in the panel, Yorgos, do any questions, or I have a couple here that I wrote up. Oh, yeah.
I have a couple of questions if I have time. These were all very interesting talks and gives us confidence for the development of infrastructure in the future. These were great. The first one is for the first speaker regarding the misclassification and the sensitivity that you presented. Whether you looked at survival bias and whether these are influenced because men do not live as long as women, and therefore women are longer at risk of being lonely because, well, they live longer. So an 80-year-old widow who has been widow for 10 years is not the same person as a 80-year-old man who is for 10 years. They're very, very different.
Yeah.
So the sensitivity would probably be, I don't know, influenced by age.
Yes, I think there are several like issues around here. So the first one is we account for differential loss to follow up between men and women by including the IPW as a sensitivity analysis in my previous paper, and the result was actually very similar. And in the second one, the marriage, whether the marriage will affect people like I think marriage will be a time varying confounder that lies on the pathway between loneliness and memory aging, and we account for that through IPTW in my previous analysis. And for this paper, when we did not look into the subgroup analysis because it may increase this computation complexity. But when we do also test whether age will affect the sensitivity and specificity values. And the good news is that we did not see much differences regarding age. So yeah, thank you so much.
Thank you. And if I have time, the second is for Margaret. So the latent factors are basically time invariant, right? So they do not move over, they do not change over time. Is that correct? Have I understood this correctly?
So essentially the latent components themselves, the Z, they just contain information that is relevant for both at baseline and also at the slopes.
Yeah.
So
can you give like some like disease specific, what is this Z trying to show?
Yeah, so the Z is essentially like a condensed information of both modalities. So the time component information will be found in the W0 and the W1, and then those Z's will just contain complementary information that is shared between the two modalities or specific to both modalities. So essentially, in a way, it's sort of like dimension reduction. So instead of now having a lot of variables and multiple modalities, you just have this one data set that you can use to do further analysis. So essentially the hope is that you can take those Z-scores and do a cluster analysis to be able to like cluster individuals based on information from multiple modalities.
Thank you.
Yeah. And then Margaret, and so I imagine there will be several applications, right? As we collect data longitudinally, usually we collect on an array of things, and then we simplify, kind of looking at this, this will be longitudinal, these are going to go, so you see thousands of papers like that, right? So your method is an advance in that we may be able to do something a little bit more sophisticated with this longitudinal, right? That's the idea.
Yeah, I think the model is, applicable to any kind of field. I mean, for us specifically, we did this using ADNI data, but any kind of data you have longitudinally. And the nice thing is that you don't have to collect your information at the same time gaps. So if modality one you collected every year, you could collect the second modality every 2 years, and the model will still be able to function.
Don't
well.
need to, yeah.
Yeah.
I want to quickly move to to Matthew, because I to have a question for him. We can't live without a question, right? All right. So you, I think very nice. You test like you had an inclusion of at least 3 follow-up years, right? Did you do you have recommendation what's the best in terms of numbers of follow-up, right? The minimum numbers of follow-up and how tolerant is the model to have a couple of people with low follow-up, right? And what's percent? What percent is that?
So a few things. First, the models can run if you just have 2 follow-up visits. What you're getting, that doesn't mean it's good, but it can produce actual estimates just based on 2 visits. What I've seen in a lot of the degradation literature is for like full identifiability of the model, you need at least 3 follow-up visits. Yeah, so this is also another sensitivity analysis I didn't show here, but we did see that some of the relative error does blow up just like a little bit when you decrease the follow-up frequency. So, but in any case, I'd recommend trying to have at least 3 follow-up visits. If you don't have that, it will still run. Just take it with a grain of salt.
Okay. All right. Any final comments? All right, with that, we conclude one more webinar. Thank you very much for presenting. It was very interesting. And yeah, we have the next one in November. Have a good day.